Okay, we are on lesson 6 of unit 5. So people who are gone for IASIS, you might have needed to listen to this video later. And it's a little tricky, so if you have questions, you should definitely get in there and see your math teacher and ask them for extra help in case you, for sure if you have questions. Anyway, you might want to pause and do the warm-up on your own. Otherwise, we can do that now. I'm going to explain it now, but you might have wanted to do it on your own first. So it says a rectangular playing field with a perimeter of 100 meters is to have an area of at least 500 square meters. Within what bounds must the length of the rectangle lie? So we're talking about the length of the rectangle. So we're trying to find the length of the rectangle, so L is really my unknown, right? So L is my length, and that should already be obvious because I used the letter. But what do we know? We have lengths and widths of your rectangle. And we know that we were given the perimeter, and twice the length plus twice the width equals your perimeter. So the width is what we're going to solve for in terms of L. So 2W equals 100 minus 2L. Therefore, the width is going to equal 50 minus L because we're going to divide each side by 2. So this W length is now the width is now 50 minus the length. Okay, then our next part says that we have an area of at least 500 square meters. So my area is equal to, well, it's not equal to, it's at least. So at least means greater than or equal to. So it has to be greater than or equal to 500 square meters. Well, how do we find the area? We're going to find the area with respect to my length. Area is everything in between, so how do we find the area? We do length times width, right? So length times width is greater than or equal to 500, but we have to have the same variable. So instead, we're going to do length times 50 minus the length is greater than or equal to 500. Now you can graph this on your calculator, right? You can see where the left-hand side intersects. So you can put this into y sub 1 in your calculator. Then you have your right-hand side. You can put that into y sub 2 of your calculator and see where they intersect. So go ahead and pause. I would pause the video to do that now. I'm not going to show you that, right? But I will sketch a picture of the graph. So we know you're going to have a 0 at 0 and 50 because that's my left-hand side. That's the graph. Then my right-hand side is going to intersect at 500. So here are my two intersection points. If you were to graph that on your calculator, you would see that one of the places that it intersects is 13.820, and the other place that it intersects is 36.180. So the question says, within what bounds must the length of the rectangle lie? So the length of your rectangle must lie between 3.820 meters and 36.180 meters. So somewhere within that bounds. And that's it. All right, so this lesson is about optimization. So our polynomial optimization says polynomial functions can be used to model real-life situations involving quantities like area, volume, distance between objects, or revenue and income. Typically, we will deal with a constraint and determine how it can be optimized, so a maximum or a minimum under the given restrictions. So when optimizing functions, it's helpful to start with the primary equation that focuses on the variable to be optimized. And so let's try it. So it says example number 1 here. Determine the area of the largest rectangle. So again, we're maximizing here, right? The largest rectangle that can be inscribed, so inside a circle of radius 4. Great. So they've told us this circle right here has a radius of 4 units. But we have this rectangle inscribed in the circle. Well, the nice part about this question right here is that it's centered around the origin, right? So that's my origin. So to get to this point out here on any point of the circle, we're going to go to the right so many or up so many. We're going to go some x units and then up some y units. So I'm specifically choosing this point right here because I went across x units and I went up y units. So what did I create there? Well, I created 1/4 of my entire rectangle, right? This first rectangle here is the same size as this green rectangle is right here, which is the same size as the red rectangle. Oops. And then my purple rectangle. So I have 4 rectangles that are the same, which have dimensions of x times y. Okay, well I don't want one of those rectangles, I want all 4 of the rectangles. So how do I find the area of this entire large rectangle? Well, if this right-hand side is x, so is the left-hand side. If this right-hand side is 3 units, the left-hand side is also 3 units. If the right-hand side is 3.7 units, the left-hand side is also 3.7 units. So in other words, we know that this entire length right here is twice the x-coordinate from the center out to here, and this entire height is going to be twice the y-coordinate. So the area of the rectangle is equal to 2x times 2y. But we know we can't have 2 variables, so we can't have the area of the rectangle and have 2 different variables, and we're not going to be able to solve it. So we need to change one of those variables. So I'm going to solve with respect to x, which means I need to change my y value into something with respect to x. Well, what's the only other information we were given in the problem? We were given that the circle has a radius of 4. So that radius can be drawn conveniently from the center out here to this point, and that is the diagonal of this rectangle. May or may not be significant, but that's what we know right now. So we know that this is a point on a circle, so let's go back to that fact. That's going to be more helpful. It's a point on a circle, and it has a radius of 4. The equation of a circle with at center at 0, 0 is going to be x squared plus y squared equal to 4 squared. So x squared plus y squared equals 16. We are trying to isolate our y to get an equation for y with respect to x. So we're trying to get y in terms of x. So I move my x squared over. I take the square root of both sides. Remember, when you take the square root, we should have 2 answers. So we have our plus and minus. So in other words, y is equal to plus or minus 16 minus x squared. So this is our secondary equation right here, which was talked about, up here. We have to create a secondary equation based on the constraints to substitute back in to our original equation. So now we have the area with respect to x equals 4 times x times the square root of 16 minus x squared. And we are going to graph that. So now you're going to take some time to graph that in your calculator. Right, so graph that in your calculator. I'll sketch the graph here. Sorry, I'd pause now and see what you get. Okay, so I have my zeros. I have 1 0 at 0. I have 1 0 at 4. I am maximizing. I'm trying to find the largest rectangle. So I'm looking for a maximum, right, which I'd put up there. I'm looking for the maximum. So the maximum occurs when my x-coordinate, or my width, half of my width is 2.828, and it says determine the area. So the area is your y-axis, right? So this x-axis was the x-coordinate length, and the y-axis was the area of the rectangle. So my answer then is that it is 32 units squared. So that's what my area equals. All right, that's great. That's page 1. You should get, I would pause now. Oops.